All right. So in the past few lectures, we have been learning about a new way of analyzing if our system is underperforming or if our application already maxing out the performance. So and this new model is called the roofline model. So it's complementary to other like quantitative analysis tools that we have learned for computer architecture in a way that it helps us to know a few things, right? So by this a few things, it helps us to know, given where our data sources is and where our, so for example, the data source can be in the cache, can be in the DRAM, and where our target computation unit is, for example, if it's CPU, if it's GPU, or even TPU, and combine that together, given the algorithm operational intensity, what's our like expected performance should be. So for example, if you have an algorithm like measures multiplication with the operational intensity like 0.25 on this plot, it should be the axis of x-axis of log -2. So if you are having, no matter what kind of computation unit you have, it's pretty much determined by where you put your data. So in this way, you will know that, well, if I'm just doing measures multiplication by itself, right, then it's pretty much more important where I perform, where I put my data rather than where I perform the computation. However, if you have an optimized code, right? However, if you are having LSTM, so some people might be curious about like, okay, so for LSTM, isn't that just also measures multiplication? But don't forget, in machine learning, it's typically the case that we read data once, and then we perform many times of the measures multiplication before we reach to the next phase when we need to read the data again. So for example, when you keep updating, you have to typically do a forward pass and then back propagation. And that's many, many runs of the computation before we synchronize the data again. So that's why even though for LSTM or many other like convolutional neural networks, it seems like you might think about, okay, the one pass of the forward or backward back propagation, it sounds like it's only a low intensive operation like measures multiplication. But if you have multiple of them where you have to do many times, then this whole computation becomes really intensive. So another implication that you might get is that, okay, if today the nature of this algorithm itself has very low computation intensity, and if right now I'm memory bound, a way of making it more computation bound or increase the operational intensity is that before I have to read data again, by any chance can I do as many operations as possible before I need to read the data again, right? So that's another way that you can optimize your algorithm to increase the computation intensity, by which it means that you could potentially make it more compute bound rather than memory bound, right? So, but let's set that aside, right? The most important thing about the roofline model is that if I know this is the computation intensity of the algorithm itself, it helps us to identify if we have reached our optimal performance, right? And the hardware accelerators, they would help lifting the ceiling up. But by lifting the ceiling up, it has multiple meanings. First of all, it means that it does increase the maximum performance of the system, not the application, not necessarily the application. The top performance of your application is still determined by the critical path of your computation intense operation, the most optimal, the highest computation intensity. So for example, if you are never possible to increase your operational intensity and shift it to right, then there is no way a better computation unit can help your performance, right? So if you are having a low operational intensity, then on the other hand, you're always bounded by your memory bandwidth or your memory performance. So what does that mean is that if you really have an algorithm or some kind of workload that you can never increase its computation intensity. So for example, if today what you are doing is just something like grep, regular expression, then those operational intensity are pretty low, then you probably would think about near data processing. However, if you have an algorithm where you can potentially do multiple passes of operations on the same set of data again and again without having the need of accessing the memory, then you can make it a higher operational intensity, make better use of your computation, a better computation unit, right? So that's another way of looking at the roofline model. But more importantly, as we mentioned, the most important factor about the roofline model is that it would help us to identify if our program has reached the roofline. So this is a demo that I should be given a while ago. So remember, in our modern computer system, so let's say like the GPU that we have, we pretty much have like around like 300 to 400 gigaflops. And the L3, it would support like 100 giga elements of data if you divide it by 4, if it's floating point, right? And if you have, if you are able to put your data in L1 and L2, then you can potentially double up that. So what I want to say here is that if you combine this all together, if you are using the CPU and you are able to optimize your code to leverage L1 and L2, 250 to 300 is a very reasonable estimation of an optimized code, right? So let's say in modern computer systems, like in Intel processors, we pretty much, so a lot of cases, right, like I would say like in CS277, right, we try our best to teach you how to implement the meshes multiplication. But to be honest, if I am an ordinary programmer, if I am a very like entry-level programmer, or say like if you are not people who work at the level of the library itself, I would say if you just want to use meshes multiplication, don't reinvent the wheel yourself. The best practice for now is to leverage libraries like this C+GMN, which Intel MKL will provide. So what does that mean is that a lot of a lot of cases, you guys are thinking about, well, I should implement my own GMN. It should outperform Intel GMN. The answer is never. Never. Because in their documents, there are a lot of hidden facts they don't tell you. So it's very impossible for you guys to beat NVIDIA's cuPlus on GPU, to beat Intel's GMM on Intel processors. There is a reason why we want to teach, why we want you to optimize those performance on Intel processors or NVIDIA processors for educational purpose. Because what if today you're implementing an algorithm that Intel or NVIDIA doesn't provide? That's the only reason why in the class we want you to try matrix multiplication, because matrix multiplication is easy enough for you to understand, easy enough for you to optimize. However, in real practice, if you're in a company, never try to implement your own matrix multiplication library unless you are inside Intel or NVIDIA. So what would typically, so if you want to use like C plus GMN, typically they would have their own library of storing matrices. So that's why we have this MKL allocate, MKL free, which would help us to implement the to store the data structure. And as you can see, here we are trying double floating point precision. And let's see what kind of performance we are getting. So let me compile the code, and then let me run this. And for here, I'm only calculating the time for the matrix multiplication, and as you can see, it finishes like a flash, right? So the gigaflops we achieve is 364. So it pretty much means that the Intel MKL library, they did a pretty good job in maxing out the performance of your Intel processor. And the number that you might, I don't know if some of you have that question, because previously I said, well, it's 250 to 300, right? But that's a previous generation of the Intel processor, and this is already an upgraded machine, so that's why it's higher. Okay, so how about the GPU? So as we know, right, GPU is another unit that would lift it up the roof line. So here's the thing: if you just look at the GPU itself, the GMN kernel itself, it actually gives us like 600 with the size like 2K by 2K by 2K. However, the interesting thing is that the GMN library of NVIDIA, and based on the NVIDIA architecture, if you just give this size of matrix, it won't max out the flops. In fact, if I can increase the size of the matrix like to 4K, right, then it will go to 4.7 teraflops. And if I can max it out to like 8K or even 16K, right, then it will go to like 14 gigaflops. And well, I tried to do like a 16K by 16, and apparently the on-device memory is not enough, right? But one thing that you can learn from this GPU in particular, because this is a 4700, right? So so you only have like 16 gigabyte of the memory, so that's why the 16K by 16K won't work. But here's the thing: on NVIDIA GPU, pretty much like if you can try a larger matrix size, then you are going to win, right? However, if you are having a smaller matrix size of matrix multiplication, saying that I only want to do small scale of inferencing, then what will happen is on the Intel GPU, the end-to-end latency, Intel CPU, the end-to-end latency is only 0.7, but on the GPU, the whole amount of time that you will pay is probably like 3 seconds, right? And even though the matrix kernel itself is really fast, but the overhead of sending data is really large, right? So but the thing is that overhead is somewhat mitigated when you have larger size of the matrices. For example, like it still take about like 3 seconds end to end to perform like 4K by 4K, or 3.1 end to end 8K by 8K. So what does that mean is that if you have a larger matrix then as you can tell, right, in terms of the end-to-end latency, the GPU doesn't increase a lot. And the other thing is that you will see the flops we got for the kernel, it better matches the roofline that we have, right? So one thing that you will learn here is that for small size of matrices like 2K by 2K is good enough to reach the roofline of your CPU. However, beyond that, you should try to think about like using GPU, right? So because of that, as you can see, right now we are pretty much in a phase that our computer has various types of hardware accelerators to accommodate different types of jobs. And for machine learning workloads, because if it's a really optimized machine learning workloads, then it's a sequence of tensor operations. So just simply optimize for matrix multiplication is not enough. And the other thing is that these operations, you can further optimize them, it will be more energy efficient or space like area efficient. So that's why Google, they start to have this TPU. And because of the success of the TPU, a lot of people are also building tensor processing unit, a similar architecture as tensor processing units. So today we are going to talk about some recent developments of the TPUs, and we are going to talk about some other accelerators, and finally to think about to see if we have time to talk about another paper. So the recent advancement of TPU. So this is TPU v4. I'm still waiting for more detail to come up for the 5th generation of the TPU and even the 6th generation of the TPU. However, so from the paper you read and this photo of the TPU, you can see like the TPU v4, they actually change a lot compared against others. And one of the things that they especially focus on is the capability of connecting multiple TPUs together, right? So the reason, and this table gives you a very good idea about what's the difference among different generations of TPU. So one of the issues with application-specific ICs is because when the application changes, your hardware doesn't change. So you really need to upgrade your hardware to accommodate the demand of new machine learning workloads. So like in 2016, the 1st generation of the TPU, as we have seen, is focusing on the inferencing. And because it's focusing on the inferencing, so their design is pretty like low precision, like 8-bit. And at that time, as you can see, the machine learning model they are using is pretty much like a multi-layer perceptron or the recurrent neural network and convolutional neural network. But later on, when we talk about the 3rd generation of the TPU, it's more focusing on both training and inferencing. And then you will figure out that, well, the workload is completely different. And the other thing is that transformer is starting to have its own significance because of the demand of natural language processing, right? And then for TPU v4, which is the 4th generation of the TPU, they start to have different versions of the hardware accelerator because they start to figure out if we want to combine everything together, that's probably not to the best benefit of the company's perspective. So they start to have the training TPU and the inferencing TPU because they found that a single chip is probably not going to be satisfying for their demand, right? So they start for TPU v4, they have the v4 Lite and the v4 itself, and as you can see, one thing interesting is that in the past, MLP or the RNN, they are the most important, but in the era of TPU v4, then transformers, they are more important, right? And you probably know why, right? But what does that mean is that as the workload changing, right, you should change, the hardware design has to change, right? So that's what you have to be in the application specific, if you are adopting the solution of application specific IC. So that's why Google is expanding its hardware team, and Amazon has its own hardware team, Meta has its own hardware team. Like, so, you know, like if you are struggling to find a job, maybe consider a career in hardware now. because all those companies, they need people to redesign their hardware for the next generation of applications. Okay. Ah, boy. Okay, so these are the 4 generations of GPUs, and more details you can find from their latest paper. And as many of you know, earlier this month they have announced like TPU v6 or even TPU v7, right? So there are a lot of new details, and I checked their articles, but none of the technical details has been revealed very well. So not really something that not because I don't want to tell you, it's because there are not that much detail that I can tell you about. So okay, so like for companies like Google, their business model is pretty much that we build a TPU, we only allow our customers and internal tools to leverage the TPU. So some people were asking about, okay, if I want to do a project with called TPU, what can I do? So the only thing I can tell you is that go to Google Cloud and start an instance, pretty much like a cloud instances, and make sure that your backend is one of the TPU instance. And how can you program it? So some people were thinking about, are we going to provide are they providing the low level like C programming interface that reveal their hardware and software interface? The answer is no. The only way you can use TPU right now is to use either the TensorFlow or maybe PyTorch. I'm not super confident about how PyTorch is compatible with TPU. Another option is probably go through JAX, JAX. JAX. That's the other option that you can use. You can leverage TPU. But other than that, it's pretty exclusive to Google itself. And the same thing as Amazon or Meta's AI ML accelerator, and they have their own compiler team to translate their own internal code to leverage those hardware accelerators we have. So again, if you want to work for those, right, you should take a compiler class, specifically ML compiler class, to gain some experience for that. And this is this is an area that I think they are still missing a lot of human resource right now. However, as I said, right, those companies, they don't sell hardware. And there are also companies that are selling hardware. They are aware that, okay, if all software companies, they are building their own hardware, then we are going to lose our business. So in response, NVIDIA Turing GPU started to accommodate a lot of application-specific ICs. So, oh wow. So basically, I think I kind of like go to talk about, so if you look at the NVIDIA architecture, the Turing architecture, and in fact, after the Turing architecture, the consumer class of the GPU, they typically would have these 3 elements. The first is the CUDA cores for vector processing. So what you have learned in CS277 or E217, that's pretty much talking about how to program on the CUDA cores. And the CUDA cores, they are vector processors, and they have vector processing model. They are really good for addressing the vector problems. However, on the Turing architecture, they also have the tensor cores designed for AI and RT cores designed for VR and AR. So let's take a look at the tensor cores. So tensor cores, if you look at the architecture, it's pretty much like this, and this is a figure graph from your paper, right? So it's part of the so this is okay. So this is subcore. This is a subcore of NVIDIA Turing architecture. So by subcore, you can pretty much think about this is a string multiprocessor, and this is one of the subcore of a string multiprocessor. So this whole thing, itself is a string multiprocessor, and in each string multiprocessor, they have 4 different hardware units. And each of the different hardware units, it contains a tensor core as well as many other floating point 32 cores and 6 integer cores. And this one, they details the amount of the capability at the same time. But like for this FP32, it pretty much tell you it's like 16 elements per core, and this is like 16 elements per core, and this is 4 elements per core, right? So this is so if you combine this together, you can see that for each stream multiprocessor is capable of doing 64 vectors at each clock cycle. And for the tensor cores, it's FT16 and 32 per clock cycle. So what does that mean is it's capable of processing, for example, like 8x4 or 4x8, this kind of result at the same time, right? So this tensor core is essentially like it supports like FP16, integer A, and integer 4. And if you look at the precision, this is pretty much designed for AI/ML workloads because they don't actually need that part. Well, in terms of inferencing, they don't really need that kind of really high precision. So this is another view of the tensor core Turing architecture. So as you can see, another way of looking at the Turing architecture is that they have integer 32 vector processing units, FP32 vector processing unit, and tensor cores. And also they have the RT cores, which we will talk about that later. So the reason why they have tensor cores, again, right, if you remember what we have been talking about using vector processing units for meshes multiplication, its complexity is pretty much n times log n in terms of hardware. However, if you are able to leverage tensor cores, systolic array, then you can reduce the complexity to linear to the size of your matrix. So tensor core architecture, they don't actually advertise themselves as systolic array. And in fact, systolic array is just one way of implementing meshes multiplication. And for tensor cores, their hardware architecture is pretty much focusing on a small tile of meshes multiplication. I don't know what's the real rationale why they do make that decision. Probably because of the area efficiency and the utilization of the memory, and the nature of your meshes multiplication can be impressively parallel. However, unlike Google, they try to implement like 128 by 128 meshes multiplication or 256 by 256 meshes multiplication. What tensor core offer, they are offering in each of the subcore, they are only doing this 4x8 by 4x8 by 4x4, this kind of meshes multiplication, instead of like a really large meshes multiplication. So to that, what they really implement is logic like this. So each cycle, so if you remember the systolic array architecture, at each cycle, we are still kind of like receiving a row or a column at the same time, but just because of the systolic array itself, you can actually do multiplication and while you are propagating the number. So at the end, the throughput would go up, right? However, what NVIDIA really tried to do is a different approach, that they brute forcefully implement all the arithmetics they need for a small tile of meshes multiplication all once at the same cycle. So what does that mean is that as we heard, right, if I want to do a meshes multiplication, like say 8x4 by 4x4, right, then what I would do in systolic array is that every cycle I would take a row of like 8 elements and a column of 8 elements, and then and in the next cycle I would take another one, right? And so every cycle I'm outputting pretty much outputting a row and a column result. That's at the end for the systolic array. But what NVIDIA architecture is doing is more ambitious in a way that every cycle I take the complete content of this 8x4 matrices and the other like 4x4 matrices. So as you can imagine, at each cycle, I'm actually taking all the pairs, all the numbers that might potentially be multiplied. And then I generate result all at once. So that's pretty much what NVIDIA architecture is doing, right? So what does that mean is that every cycle, I'm taking all the numbers. For example, if I'm doing 4 by 4 by 4 by 4, what they are doing is that for every cycle, I'm just doing all this kind of multiplication and generate result all at once. So it would actually reduce the amount of cycles that they need to produce the matrix, the result. Right, so that's the tensor core architecture they are doing. So it's not really a systolic array. It's a brute force implementation of all the arithmetics and try to finish matrix multiplication in just one cycle for a small tile of matrices. So that's their philosophy of implementing the hardware. So, so you can pretty much imagine if I have a hardware architecture that performs 4 by 4 by 4 matrix and multiplication and accumulation in one cycle, each tensor core is capable of doing equivalently 128 floating point operations per cycle, right? So with that, if I have an 8 by 8 by 8 matrix multiplication, and that would trigger this amount of floating point operations, right? And with conventional CUDA cores, so for example, in Turing architecture, you have this amount of CUDA cores, right? So if this amount of floating point operations we divide it by the amount of CUDA cores we have, then this is the amount of CUDA core cycles that we would need, right? So this is the estimation of the CUDA core performance optimally. However, if you have tensor cores, in Turing architecture, we have 320 tensor cores, and each of the tensor core is capable of performing equivalently 128 floating point operations for the matrix multiplication. Then it only requires this amount of tensor core cycles, which means it has 16 times faster performance compared against the conventional CUDA core performance, right? So that's why matrix multiplication, if you see like matrix multiplication is 10 times faster than the past, it's a significant improvement over the conventional architecture. And even for 4090, they changed the size of tensor core operations to 4 by 4, 8 by 4 by 4. So each tensor cores, if you partition that size correctly, then it can perform like 256 floating point operations. So you can see they still maintain an 8 time difference in terms of the CUDA core and tensor core performance in 4090. So and this is the tensor core architecture. Okay, so another kind of cores that NVIDIA GPU provide is this ray tracing cores, RT cores. So ray tracing is an algorithm pretty much like this. So its idea is that it tries to emulate the physics effects of lighting in real life. So what would happen is that we would assume this Bart is the user, right? And then so right now you can think about like you are the Terminator or some like superhero, right? You shoot a lot of rays out from your eyes, right? You examine the world through the rays you shoot outside of the world, and each of the ray would have an intersection with your screen, right? So that's where your monitor is, right? And then after that screen, you can imagine you have a lot of objects. For example, the bell tower, and there are some light sources like the sun, and between the light sources and the object that you see, there may be some other objects with some other phenomenon, right? So what will happen is that this kind of objects between the light source and your object, they will create shadows, right? And they would also have some reflection of the lights going to the bell tower, and there are also some direct lights go from the sun to the bell tower. So synthesize all these lightning effects together. This algorithm itself is trying to calculate what's the color intensity that you will see in this particular pixel. So that's a different approach of rendering in computer graphics. So the traditional approach in computer graphics do not consider this lightning effect at all. It's considering from the user. So okay, so I would say this is more like a physics simulation, but the conventional computer graphics is more like painting, in a way that we assume this is the canvas. Your screen is like a canvas, and the painter, or say the graphics designer, they decide what the user will see by coloring each pixel, right? So they describe what color of the pixel is through a set of algorithms. So it's a different way of thinking about rendering, right? So this is from a more physics simulation perspective. So as you can imagine, right, the painters has limitation. Of course, there are arts, like the effect of arts inside, but in terms of the real life experience, this way is definitely better. Okay, so then why? So this is an algorithm of a simplified algorithm of performing this physics simulation. So now I'm going to ask you a question. Why not just use CUDA cores or tensor cores for ray tracing? Why we still need an RT cores? Here are some cupcakes. Feel free to take them. And also coffee. What? How is the intersection of the? You can imagine, like, you probably have some description about what's the size of the object, where the coordinates of the object, and the direction of your ray, right? And you can decide if there is an intersection or not. I was wondering if like they decided to like represent that kind of like searching a graph, finding the intersection as like, well, that's a very good idea to think about, right? The answer is yes. Okay. Yeah. All right. So how many of you took 217 before? Okay. Many of you took 217 before. So you must be familiar with GPU programming. So for this pieces of code, what do you expect we could do it well on CUDA cores? You can naively distribute the for loops into like threads. Mm-hmm. The hard part is just the if statements. The if statements. In what way? It's hard to get a group of like Right. So here's the thing, right? If you look at the behavior of this pieces of code, okay, so in the very beginning, you might be thinking about, okay, this is a real good candidate for CUDA cores because I see for loops, right? And whenever you have for loops, it seems like parallelizing each CUDA thread for each iteration within the for loop seems to be a good idea. Then when you go into this side for this for loop, you will figure out, okay, it has if statement, right? And for the if statement, it's performing another function called intersection. That's fine. But some of you did mention that what does that intersection do, right? So we will talk about that later. But the basic idea of the intersection here, as you can imagine, that's why I have that slides pull up in the very beginning. The idea of intersection itself is considering if the ray would hit an object within a scene, right? So if you think about how are we going to describe objects in a scene, right? It's pretty much like you have to build some kind of a data structure to describe and organize this object in a scene. So for example, the most commonly used data structure is bounding volume hierarchical tree. And the bounding volume hierarchy tree is pretty much like here. So saying that these objects, they are the ones we have in a space, right? And then the bounding volume hierarchy tree is pretty much we group the trees together inside inside different levels. So the top level should contain everything, right? So that's called that's a very first bounding box that contains all the objects that we have in the scene. So if today I have an array that doesn't really intersect with the whole box, you don't have to go through the rest of the process, and then you can directly return, right? However, if there is an array going through this box, then it's really important that we figure out if it would intersect with some of the objects within this big box. So that's why we also have the next level groups that we try to build a binary tree that gradually separate out groups of objects. So for example, the B1 tree itself may contain these objects, and further we can break up these trees into different sub-nodes, and then they will eventually contain the leaf nodes, which is our objects, right? And the same thing we can do on the right-hand side. So gradually we build up this bounding volume hierarchical tree. So what will happen is that today, if I have an array that only hits this part, I don't need to check anything on the right-hand side, right? So that would save our time, and this would reduce the search time to log n of your objects, ideally, if you have a balanced enough tree, right? So that's the idea of bounding volume hierarchical tree. So, but can we do tree traversal very well on CUDA cores? The answer is not, right? So that's why, and that's actually the main reason why, one of the main reasons why CUDA cores is not a good fit for this workload, because the intersect itself is difficult for the CUDA cores to do. That's just the first. And the second, many of you already identified. Even though, let's say this is simple enough to do, right? Then it becomes problematic in a way that after that, we would trigger different operations. So for example, if object equal to null means that there is a hit, then we are going to call this function. If it's in a shadow, then we are going to call this kind of computation. Otherwise, it would just have a 0 pixel, right? So it means that there are many multiple possible operations that we need to perform based on the result of intersection, which is difficult to create a so-called regular workloads to be within the same stream multiprocessor. So that would pretty much waste a lot of cycles in your GPU, right? So those are the reasons why this is not a good fit for GPU. So, and here is another way of looking at the ray tracing pipeline. So the idea of ray tracing pipeline is that in the very beginning, the code would generate rays from the user's eyes. And then we will perform a sync traversal using the accelerated bounding volume hierarchical tree to see if there's a hit with the object from the array. And based on that, we would potentially have different functions that would be triggered. So for example, if in a first sync traversal we don't find any hit, then we will go to a close hit shader. If there is a miss, then we will go to the miss shader. And if we decided the light would not propagate further, then we will go to the close hit shader. Otherwise, it will continuously test if there are other intersections and try to trigger another shader. So there are basically 3 different types of shaders that you would trigger in ray tracing. And it creates a few like control divergences that you won't be able to accommodate very well in CUDA cores. So here is the hardware solution NVIDIA provides. So they basically made a ray tracing accelerator to accelerate the sync traversal and the intersection test process. And after that, they are able to figure out what kind of shader functions we are going to trigger. So from the hardware perspective, there will be another scheduler take those results and then dynamically schedule those shader functions in, or say group those similar shader functions to the same stream multiprocessors, so that you can still leverage stream multiprocessor to perform the same function and create regular workloads. So the ray tracing process would be able to better utilize the CUDA cores while leveraging the hardware accelerators for intersection test. So that's another type of accelerators that NVIDIA have now, right? So the reason why they need that is because there are real-life applications that they really need, like VR or AR application. We really want, or gaming, right? In fact, right? If I talk about VR, AR applications, you probably don't have anything in mind. But if we talk about gaming, you must have something in mind, right? Or for gaming, essentially, because don't forget, like gaming is still one of the largest market for NVIDIA, right? So they need to take care of that. Okay, so that's part of the hardware acceleration they have done now, right? And if you check the recent development of NVIDIA GPUs, they start to support other data types. Like for A100, the M-Sphere architecture, they support TF32, and H100 they also support TF32, which is I would say is a 29-bit floating point representation, which allow higher precision in training. And for A100 and H100, they even support FP64 because they also see there is a demand for scientific computation. Although NVIDIA didn't say very clearly about what kind of hardware architecture they use to perform this FP64 tensor core operations, but as the performance number revealed, we did some reverse engineering with that performance number. We kind of like suspect what they did is that, so one thing that a lot of you might already know, right? So some of you might be curious, okay, what's the meaning of more advanced technology if we cannot power on all of them? The answer is that within the same chip area, we are able to fit in more hardware units, even though we don't use them all at the same time, right? So turns out what NVIDIA choose to do. So, okay, so I found a lot of you, when you are looking at this NVIDIA architecture, you are still in a phase that we should fully utilize this hardware units. But NVIDIA, when they design the hardware, they are more from the dark silicon perspective, is that we are giving you like okay, how many of you know the Swiss knives? Like we will have a lot of tools on one small tiny pieces, right? But you are typically not using all of them at once. So they are pretty much like this. Each NVIDIA GPU right now is like a Swiss knife. And when you want to use FP32, we turn on the FP32 part. When you want to use the tensor core, we turn on the tensor core part. When you want to use the RT core plus CUDA cores, then we turn on both elements. And same thing for this FP64. since we have the die area, since we are not able to use all of them, then what happened is that they built a separate tensor core for 64 precision. And only if the user want to perform 64 operations using tensor cores, those would turn on. Otherwise, it would be power off to save the power consumption. So that's the recent development of the NVIDIA. So if you check, here is the number of the floating point operations they have, and even more crazily. So we already think that the GPU cores, they are not really that good for control divergence workload. And another important algorithm that is very control divergent and also frequently used, which is also one of the most frequently appeared solution to a lot of leak code question, is dynamic programming. And so dynamic programming is notoriously bad to parallelize. And nobody can ever parallelize dynamic programming efficiently on CUDA cores. However, NVIDIA's strategy is that we want to sell the GPU to everyone, right? So how can you forget the dynamic programming? So they even have the DPX instruction extension on NVIDIA GPUs right now. However, they are only available on data center segments. So if you, so like really expensive GPUs like H100, which I don't have any, but if you have access with those, right? One project I'm really interested to see is if someone can try to leverage those dynamic programming extension instructions to accelerate some set of applications, right? But this is the recent development of NVIDIA GPUs. So what that means that is that the NVIDIA GPU is a heterogeneous processor. And not only NVIDIA doing that, Intel is also doing that, right? If you look at the Intel Alder Lake processor, they also have the graph cores, they also have the GNA accelerators, and their recent development further extend the GNA accelerator as an NPU architecture, right? So this is the Intel architecture. So beyond those GPU cores, they also have the GNA and some of the DSP connect through the memory bus. So even the Intel processor right now is a system on silicon system on chip, right? So what does that mean is that your processor there's not so I would say right now, well, I would say like both Intel or NVIDIA, they are not like really just manufacturing the CPU or GPU. They are selling you this system on chips. But different companies, they have different specialties. So for example, Intel has the best CPU, but the worst GPU. And NVIDIA has the best GPU, but the worst, very weak CPU. Like some of their offering, they do have the ARM CPUs inside, right? And for AMD, they have second level CPU plus second level GPU, right? So that's the option that you can have on the market. But one thing you will find, like Google TPU, they are standalone like PCIe cards in addition to those processors. So there is a very interesting question I want you guys to discuss. Should we go the SoC way or a standalone accelerator way? Okay, what do you guys think? What do you guys think? Ideas? Okay, what do you think?
What we're talking about is that if you try to cram everything into one chip, right?
Mm-hmm.
There might be some benefits, but there's also a trade-off. So
Okay, what's the benefit?
So basically, like the benefits is like less memory bandwidth, like since like they're, less memory overhead from using those accelerators since they're kind of closer to the CPU. They don't have to travel over the PCIe.
Okay, so shorter access latency, I would say, from the memory.
Yeah.
Okay, and okay.
No,
I think SoCs are easier for fabs to produce.
For fabs to produce, are you sure?
There's less defects instead of throwing away the entire accelerator.
What do you think? Yeah.
Okay, so it's not a one choice will win another. So the thing.
Oh, I thought you have some comments about that fabrication. So I would have a counter argument with that. So here's the thing. If you have a big giant chip and given the same failure rate of transistors, is it easier to find an error within a giant chip or a smaller chip? So the bigger your chip, actually, the lower the mole function, the higher the mole function rate a die is going to be. So if you have an SoC, if you put everything into a single chip, you will have a higher probability of, you will have a lower yield rate. That's basically what it says, right? So that's actually the bad thing, right? They have a reason to go with the SoC, right? So memory, but I don't think you put a very precise description on that. But I think what you meant to say is higher memory bandwidth in general, right? Because like some of the technology, if you put them on the same chip, right, you are actually allowed to have direct connection, direct access through the memory bus on the same chip. So the shorter wire, higher frequency, right? So you are potentially get better memory bandwidth in that way, right? Other thoughts? Okay,
so,
you go.
Okay, so we were also talking about that if you're not expanding the chip size, right? Then you need to make the trade-off of like how much die you're giving to the CPU versus the GPU versus any other accelerator. So the more you kind of prioritize one or the other, the weaker everything else is going to get.
Right. So, but if you build standalone, you can build a very powerful one.
Yes.
Right. So one evidence is that how many of you are satisfied with the on-chip video card performance if you are an intensive gamer? Okay, I hear that, right? So that's why even though you have like AMD CPU, for example, even though, or Intel like CPUs, they both have like video cards video functions on their chip. You never use it, right? What else?
I've had issues SoC, if you have a unified memory,
Uh-huh.
I had the page correction issue where the CPU touches a page that the GPU has, and the GPU touches a page the CPU has, and it keeps going back and forth. You have to flush a TLD, flush the cache.
But isn't that the same issue as standalone accelerator?
Well, usually standalone, you have a separate memory space.
Okay, so the unified memory space, that's one issue. Can you, and is that the only issue if they are sharing the same memory interface? What else? More essential issue with that? Bandwidth in what way? Okay, right? So pros and cons, right? If it's a single chip, you do have larger memory bandwidth. However, it also means that for this particular memory bus, now you have more competitors, right? So take a look of the Intel architecture, right? So this is the architecture that Intel shows in their paper, right? Look at this, right? All the CPU cores, the GNA accelerators, the DSP, they are all competing with the same memory bus, right? So in fact, larger memory bandwidth, but also higher competition. So what if right now every of them are thinking that I have a critical job, that I really need exclusive memory access at this time? Then some of the workloads may be delayed. And for the unified memory issues that Andrew talked about, right? In fact, if you look at this, this is solvable with an SoC. If you look at the architecture that Intel shows, is that the GNA accelerator and the DSP, they have their own SN area on the SoC. So that's a solvable problem. Like you can just have like separate caches for each hardware unit. However, the real problem here is that at the front end, those chips themselves, they have limited storage, right? So there must be a case where we are going to access some of the shared area. And when we try to access those shared area, it's the same front end that we have to compete with. And even worse, right? For GPU memory, we want high bandwidth. But for CPU, we want to have low latency, right? How are you going to accomplish both with the same memory controller? Right? More access ports, but then higher cost, right? And more difficult to arbitrate, right? What else do you guys have in mind? Okay, so that's actually another problem, right? That's why you see those NVIDIA GPUs right now, they go up to 700 watts. Why? Because we have so many functions together, right? And although we do mention we can possibly turn off the transistors, but none of the circuit design, none of the circuit is ever perfect. Although we think we are closing it, but we are actually not going to fully close it, because if we do that, when we want to power on it again, there will be a huge overhead for that. So typically we just put in a really low voltage. So what does that mean is that given the amount of transistors that you have, as long as you are supplying it with really low voltage, it's still leaking power, right? So the more transistors you have at the end, you are getting higher power consumption as well, right? So it turns out you see the heat sink of NVIDIA is getting hotter and hotter, right? Because of that. What else? Right, so those are the good discussions, right? So first of all, on the positive side, in a single chip, the good part is that we can reduce the system interconnect bandwidth demand, right? However, the system interconnect is you still need to have some kind of system interconnect, but instead of using copper wires, they are right now the silicon wires within the same chip, which is shorter, faster, and reduce the total system size and cost. You guys didn't talk about that, right? So where is the best place for this system on chip in play right now? especially for Intel, why they built this kind of chip? Because like your laptop, that's what we really need. We just need one chip that has everything. And like you are not supposed to play like intensive game using your laptop, right? So that's why if you are talking about gaming laptop, none of them really look as stylish as like a Mac, because you really need a big space. You really need like a separate GPU to make that happen, or more space for the heat pipe, right? But to be honest, right, the main thing about the good thing about system on chip is that if it's a small chip, right, it can fit into a mobile phone. It can even fit into your watch, right? So you don't really need a lot of separate chips to produce, and they have a lot of functions that fulfill the user's demand. So that's the good thing about system on chip. And however, there are also other problems, like the design of memory controller is very complicated. One of the paper has been talking about this, and the power consumption per chip is still limiting the overall performance, right? Like that's what AMD end up with. It's not because AMD cannot produce really high performance processor. It's just because AMD strategy is that we are going to provide a better GPU performance than Intel is offering, right? So turns out if you consider the whole chip power consumption, then what you can only do is like somewhat slower CPU performance, but a lot higher GPU performance for their users, right? So if you are a gamer, well, I would say a moderate gamer, you are going to satisfy with that AMD offering, right? But another problem is that how many customers are in that segment, right? So that's the maximum amount of consumer they can get, right? So the thing is like it gives you a balanced design, but it never gives you an optimal design if you are going with the system on chip way. So one of the company that is really greedy is called NVIDIA. So they just choose to that their thermal design point goes up a lot, right? Packaging goes a lot to like 700 watts, since there's nobody offering that kind of performance in the GPU segment. So they can just sell it. Heatsink, that's your problem, right? But if you talk about like a standalone design, right, the heatsink is going to be easier, right? So, but even though, right, you still need heat pipe for like TPUs. And also the system size is larger, cost of ownership can be higher, right? And data movement going through the system interconnects is a little bit of the problem. Okay, so the thing is that with this many accelerators, how are you going to program them? So this is the programming interface for Tensor cores. So if you really want to program Tensor cores in a low level, you can actually use this WMA standard library interface provided by NVIDIA. As long as you install CUDA, it's in there. So as you can see, in the very beginning, which is the pink part, you need to allocate some of the NVIDIA WMA data structure, pretty much specify your matrices and your result matrices, because result matrices, they are in different ways. And then also, you need this blue part to load your matrix data, and then the red part, which is performing the real MMA operation, and then store the result back using the orange part, right? So you can see this interface itself, right? If you really want to use tensor cores, instead of writing, so in the past, when we talk about matrix multiplication, you are writing like a three level at least nested for loop to make that happen. But in the era of NVIDIA CUDA tensor cores, what do you really need to do? If you really want to control the tensor cores in a low level, the finest degree of operation is actually at the MMA. So you don't need that kind of for loop. Instead, you have to think about how can I leverage that particular matrix multiplication and accumulation. And if you don't program it this way, it's not possible for the NVIDIA hardware to leverage that, right? And another way that's, again, easier to do is that you should just code cuBLAS GMN, right? And the cuBLAS library itself will figure out, right? And, you know, another company called Intel, I don't want to say too much about it, right? But the thing is, like, they also have this like GNA accelerator, and again, if you want to use a GNA accelerator, you have to use their particular API interface to trigger those operations that GNA supports, right? So how do hardware accelerators change our programming paradigms? What are the benefits and limitations of the new programming paradigms?
But then again, like we're not moving past from learning like just general C++. I need to learn every specific cellular kind of like programming to get it. What was nice about it is CPU version is it's very transferable. You program, if you know how to program like it's very you know what you want to do. Now GPU value when GPU value
Not only gives you a programming task, it increases the complexity of your code to make it work.
yeah, it gives you a lot more kind of like low grade material. And so like that's what you got like now the programmer got to take more idea of what the hardware is actually doing, what the actual physical limitations of the hardware. So again, like that gives the benefit of like if you know how to use it, great performance, right? But as you said, it's just harder now because everything is so unique to its own thing that every new hard accelerator has its own kind of like programming like kind of like paradigm that you have to learn.
All right. So as a programmer, how do you guys think the hardware accelerators are going to change your life as a software programmer? Okay, what do you think?
It's going to make our lives a lot more difficult.
A lot more difficult. In what way?
Well, what I was talking about with Andrew was the idea that now, say you're trying to make portable software that like a user downloads, no matter what their machine, it's going to run, and it's going to run as efficiently as possible. You now have to figure out all the possible combinations of hardware that they could be running and then support that in the code. And each of those probably has a different API interface that works entirely differently. So that makes your life a lot more difficult.
Right. So the thing is like, okay, so that's a very good observation. Your life becomes a lot more difficult because right now you have to ask the company, what's the specific hardware we are targeting? What kind of GPU are you targeting? Because one thing you'll be aware is that, okay, NVIDIA use CUDA, right? And AMD, they use their own dual chain, the ROCm dual chain. They have their own ROCm interface, plus they have the HIP interface, which I really hate its name, HIP, right? It's called HIP. And the thing is, like, they do provide a tool called hipify, that you can get a CUDA code and translate it to HIP function codes. But no matter it's CUDA or HIP, right? That's only exclusive to NVIDIA or AMD architecture. And once you decided, it would take some efforts to go to another platform, right? So that's actually the ecosystem that NVIDIA is trying to build. They are trying to attract as many people as possible to use CUDA. And then once you have your code in CUDA, lazy programmers, we don't want to change. And the other thing is that in production system, we should not change that because we don't know if there's going to be a new bug after we modify the code, right? So once the ecosystem is built, it's very hard for you to migrate, right? On the other hand, it means that, first of all, you have to write a program depending on what kind of hardware you have, and you should be aware of that, and you should optimize for that. And once you have done that, if anything changes, sorry, you have to rewrite your program, right? Or you should just keep using the same hardware, right? So that's what NVIDIA is trying to do, right? Because right now, a lot of the reasons why we're still sticky with the NVIDIA solution is because we have chosen that. We have chose that, and we cannot change. If we want to change, the cost is that we have to rewrite everything, right? What else? So that's the limitation. But what's the good side?
The good side is like if you can actually utilize it properly, you have better performance if you have the workload to support.
Right. So the basic reason why we want this new programming paradigm is that if we are able to rewrite our code using those API functions, then it's going to be higher performance, right? On the other hand, I will also argue it will make the programmer's life easier. So right now, all you need to do is look up the document to see what kind of operations are supported by the hardware directly. And I should try to invoke those functions as much as possible, right? So in the past, you need to learn a lot of algorithms. But right now, maybe some of you can use DPX to write a dynamic programming software, right? So just give me the input matrices and what's the desired output and what's the criteria you want to compare. With that function call, you don't actually need to implement the dynamic programming yourself. You just need to call dynamic programming, input, desired comparison, result, right? Isn't the programming easier in that way, right? But so the benefits is that programming may be easier. However, it makes the optimization once you are optimized for one platform, it's really hard to migrate, right? So, but that's so those are the things that you have to keep in mind. But as a summary, the accelerator is helping us to lift up the roofline, and with hardware accelerator, more applications are going to be memory bounded. And if you really want to better utilize your hardware accelerator, you should try to think about how can I make my computation more compute intensive. Or the other thing, on a programmer's perspective, you should try to leverage those hardware accelerated functions as much as possible, right? And other than that, don't forget to form your group and make an appointment through the Google Calendar. I already met with one of the group yesterday, and I think a lot of you should really think about the big problem before going into the project detail. And other than that, enjoy the rest of your week. I will see you next Tuesday.
Feel free to talk about, do you have other times to meet up, or is it only Wednesdays?